Okay, in this video we're going to be talking about inverse circular functions. Now this right here is a good way to help review the unit circle. Basically what you're doing is you're undoing the input of what the unit circle would take in. Well, really we're talking about sine, cosine, tangent, cosecant, secant, cotangent. We plugged in an x, which normally was either a degree value or a radian value, and we'd get either the x or the y coordinate or a combination of when we were looking for one of those trigonometric ratios, sine, cosine, tangent, and so forth. So what we're doing now is we're undoing that. What we're going to do is we're going to take a look at those values from the unit circle, the coordinates on the unit circle, and we're going to try to undo that to figure out what radian mark or what degree mark produced that. Okay, so we're going to look at a few examples, and the first example that I'm going to go over is for a sine inverse. So I want to point out here that sine inverse has a range, and all of these have a domain and a range. All right, they all have a domain and a range, and the interesting thing is that they're all typically, from, like a -1 to 1 or so. It corresponds to values on the unit circle. But the range is what's a little bit different, okay? So the range will change for each of these. And so if you're looking at a sine inverse, for example, if you see here, and I'm going to highlight it, the range for the sine inverse goes from -pi/2 to pi/2. The cosine inverse goes from 0 to pi, okay? And the cosecant inverse goes from -pi/2 to pi/2, excluding y equal 0. The secant inverse goes from 0 to pi, excluding, of course, pi/2. And remember, those are where those graphs had asymptotes, a vertical asymptote. Tangent, if you look at it, goes from -pi/2 to pi/2. Now notice it's not less than or equal to or greater than or equal to, because we have asymptotes at those pi/2 values. All right, and cotangent similarly has asymptotes at 0 and at pi, but the range exists between 0 and pi. All right. And when I say that they had asymptotes, that was the original function that had those asymptotes, the tangent, the secant, and the cotangent, okay? Or the tangent and the cotangent, I should say. All right, so let's go ahead and take a look at sine inverse of the square root of 3/2. So we know that it's going to be somewhere between -pi/2 and pi/2, which means that it's from -90 to 90 degrees. So we're only looking here at quadrant 1 and 4. We're looking here. All right, and we're going to identify where is the y value, the square root of 3/2. Well, that happens only at one point. That happens right here at pi/3, which corresponds to 60 degrees as well. So the answer here in radians is going to be pi/3 radians. All right, if you wanted a degree answer, you would say 60 degrees. All right, now let's go ahead and take a look at the cosine inverse. Now the cosine inverse, if you look at the range, goes from 0 to pi. So we're going to be looking in this window here. All right, we're looking for where was the x value, the square root of 3/2. Well, the only place that the x value has a square root of 3/2 for it is right here at pi/6 or 30 degrees. So that right there is the answer for this second problem. It is pi/6. Again, if you wanted the answer in degrees, you would say 30 degrees. And so that's how you would evaluate that one. Okay, so it's really nice, really intuitive. You just use the unit circle. Now let's step it up a notch. Let's take a look at tangent inverse of -1. So let's talk about the range for the tangent for a second. So the range for tangent inverse is from -pi/2 to pi/2, -90 to 90. So let's erase this here. We don't need that anymore. So we're going to be looking at this window again. And we're looking for tangent inverse. So we know for tangent, this is y divided by x. All right, so let's think about that. Where is y divided by x -1? That means that y and x had to be equal but opposite in sign. And the only place that I see that happening is right in this neighborhood at 7 pi over 4. But 7 pi over 4, when you think about it, you count backward. So this is right here, pi over 6, pi over 4, pi over 3, pi over 2, but they're all negative. So the answer here is that it actually occurs at negative pi over 4. All right, so it occurs at negative pi over 4. All right, or negative 45 degrees if you're counting degree marks. All right, so let's think about it for a second. What is it? It is exactly, going back to the circle, y divided by x, it's going to be a negative square root of 2 over 2 divided by a square root of 2 over 2. That's how you get the -1. So that's the tangent, all right? Maybe not necessarily what that equals, but the tangent. So then the tangent inverse here corresponds to that negative 45 degrees or negative pi over 4 radians. And that's how they came up with that. All right, so let's take a look at another one, cosecant inverse of 2. Well, this one right here, you have to remember, corresponds to what? Okay, this corresponds to the reciprocal of the sine. This is 1 over the sine. In our case, it is 1 over the y value. Okay, so we're looking for where is the reciprocal of y? All right, 2. Well, that means that y would have had to have been 1/2. Okay, so we're going to look at cosecant, and let's take a look at its range for a second. The cosecant is from negative pi over 2 to pi over 2, and we're looking for wherever the y value would be a positive 1/2, and the only place that I see that is right here at pi over 6 or 30 degrees. All right, so we know that the answer there for this one, number 4, has to be pi over 6. And so that's our answer right there. And let me change my pen color real quick. All right, and then let's take a look at number 5 here. The arctangent of 1. Well, tangent, recall, is y divided by x. So in this case, y and x have to be equal in sign, or perhaps both. Well, they have to be equal in sign, so they're either both positive or both negative. But when we know something about tangent again, and let me erase this, tangent inverse exists from negative pi over 2 to pi over 2. So we're again looking at this window on the graph. So the only place where y and x are actually equal occurs here at pi over 4 or 45 degrees. So this one right here means that we're looking at the case of the square root of 2 over 2 divided by the square root of 2 over 2, which will yield 1. And the only place that occurs is at pi over 4 radians within that range. All right, so pi over 4 for this one here. All right, now we look at another one, arcsecant, and we're going to go through quite a few examples, but they're really quite quick. Arcsecant of 1. So let's recall what the secant was. The secant was 1 over the cosine, which is 1 over the x value. Well, we're asking ourselves, where was the reciprocal of x? 1. That only happens at one place on the circle when we consider the range of the secant graph. So let's take a look at the range of secant. It's from 0 to pi. So that means we're going from here to here. And secant, again, is the reciprocal of the x value. Well, the only place that that happens on our circle is at 0 degrees or 0 radians. So the arcsecant, in other words, is going to be 1 over 1. All right, and that happens at 0 radians. All right, so there's one thing I will mention. I kind of just went straight into arctangent and arcsecant, but arctangent and arcsecant is the same as tangent inverse. It's the same as secant inverse. I believe where this came from was that when these mathematicians hundreds of years ago were working on this kind of stuff, they didn't have a way maybe to write these little exponents, these little typesets. So somebody came up with, well, let's just call it the arctangent, or let's just call it the arcsecant. So I'm pretty sure that that's what happened. But as typesetting evolved and things like that, they decided to call it what it is, and that is the inverse function with the -1 there. All right, now let's take a look at the last couple of examples where we consider degrees. So we're going to do the same process. All right, we're going to talk about, in this case, the cosecant. So we're going to take a look at this one right here that I call number 13. And I know I jumped around, but this is part of a larger set of problems. All right, so the cosecant inverse of -2. Well, let's look at the range of the cosecant. The cosecant inverse is going to go from -pi/2 to pi/2. So we are looking at this window here. And cosecant is the reciprocal of the sine. So we're looking for where was the y value. In other words, we're going to say 1 over the sine, right, which is 1 over the y, which would be 1 over some number that would give us a -2. Well, that would have to have been -1/2, because the reciprocal of -1/2 is, you guessed it, -2. So we're looking, where does y equal -1/2 on that unit circle in this window of numbers that we're looking at? Well, the only place that happens is right here at 330, or 11 pi/6. But remember, we're going from -90 to 90, right? So this one right here would correspond to what? Well, it's 30 degrees down. So -30 degrees is our answer there. All right. So the answer for number 13 here is that the cosecant inverse of -2 equals -30 degrees, and that's what we find for this. Okay, so again, it's very important to pay attention to the range of the trigonometric function that you're looking at. Now number 14, slightly more challenging. We're looking at the cotangent inverse of a square root of 3. So let's think about what cotangent is. So if I think about cotangent, I'm thinking about x divided by y. All right, and I want to pick some x divided by y that will yield a square root of 3. Well, that means that I probably have to have a square root of 3 in the x coordinate to be left with that. So let's go ahead and take a look at the range for the cotangent function. And the cotangent function is going to go from 0 to pi. So we know we're looking in this area. We know that cotangent, in order for it to be positive, it's going to have to exist in quadrant 1. And I'm going to take a guess that I see a square root of 3 over 2 and a 1/2 right here in this area at pi/3. All right, is that pi/3? Oh no, no, that's not it. That's tangent. It's this one right here, pi/6. Okay, you see the x value had to have a square root of 3. So what we're going to do is we're going to say, okay, square root of 3 over 2 divided by 1/2. What's that? All right, so let's come back to our problem here. Let's suppose that it's the square root of 3 over 2 divided by 1/2. What does that look like? Well, I always tell my students KFC, keep, flip, change. Square root of 3 over 2 times 2 over 1. And there we have it. We have our square root of 3. So where did that occur at? Okay, that occurred at 30 degrees. If you're, of course, talking about radians, you would say pi/6. But in this case, we're asking for degrees. All right. Now, number 19, very, very similar. We end up with a square root of 3 over 3. So this one right here is going to reverse the roles of that x and y, if you will. Not so much reverse them in terms of flipping x and y, so much as the order of the ordered pair changes. All right, so this one again, recall yet again that the cotangent is x divided by y. So I'm going to guess that it's going to be someplace where 1/2 is being divided by the square root of 3 over 2. And it's positive. And if we go back to our circle, we know that we're looking again at 0 to pi, or 0 to 180 in our case. So I'm gonna take this guess that it's this one right here at pi over 3. All right, because I need a square root of 3. I know it's not pi over 6 because I already worked with that. Okay, so my guess is it's going to be pi over 3, but either way, you'd be looking at something with a square root of 3, so you'd probably want to try both of those. So let's think about this for a second. KFC, 1 over 2 times 2 over square root of 3. We cross that out. We're left with 1 over the square root of 3, which is a denominator that we have to rationalize. And what do we end up with? But the square root of 3 over 3. So where did that happen at? Okay, so we go back to our circle just to reflect on that for a second. And that, of course, happened at pi over 3. All right, that happened at pi over 3, which pi over 3 corresponds to 60 degrees. So this one right here will equal 60 degrees. If you wanted radians, again, pi over 3. So this is a good look at inverse circular functions. Again, it's really important to know this unit circle. All right, it's so important. If you can memorize it, that'd be great. But inverse circular functions relies strictly on the range. So be very careful, because you might find, oh, well, some other number works. But the range is crucial to answering these questions. So be very careful, because it's very easy to pluck out a number from another place that might correspond, but is not necessarily the correct answer that we're looking for, because it's all dependent on the range. So please, please, please pay attention to this chart that I've drawn out for you so that you know about the range. All right. Your calculator, if you're asked to do maybe some kind of calculator-based questions, calculator can definitely do this for you. Just be sure that you are in the appropriate mode, whether that's degrees or radians. So, as always, I hope this video was helpful. And remember, like and subscribe.